In this section, we are going to discuss certain properties of differentiable maps that we collect in one big section, and there are basically, most of them are generalizations of results of the one-dimensional case from Mathematics 1. For example, we will see a mean value theorem, which will be similar to the one we had in the previous semester. We will talk about local extrema a bit. We will go into detail on this a bit later in this course. But yeah, we'll collect some constructions and some important results about differentiable maps in here. I want to start with a construction that was indirectly already part of this course, but I haven't given it a name, or this particular construction, namely the following. Definition 1232. So assume we have n and n, U be an open subset of Rn, and f from U to R. So a real valued function. Now, we've seen the Jacobi matrix in the previous section, and we've seen kind of the matrix representing the differential. And in this case, if this is a subset of Rn going to R to the power of 1 here, the Jacobi matrix would be a 1 by n matrix, which means a vector, a row vector to be precise. So instead of writing this as a row vector, we will just interpret this one as a point in Rn and give it a particular name. Namely, so here we only need the assumption that if f is partially differentiable in a point A, differentiable in a point A, which is an element of U, then the following vector, we denote this by this upside down triangle, which is called nabla. Nabla f of A, which is defined as the vector which simply contains all the partial derivatives as entries. It's a real valued function, so the partial derivatives on that point are just numbers, meaning if we put them all together, it is a vector in Rn. So this is dn f in A, this as an element of Rn. This is called the gradient of f in A. And I'm pretty sure that the gradient already popped up in your physics classes at some point, the gradient of f in A. And other notation that is also used for the gradient is simply grad f in A, so as a word. But I prefer this symbol, it's neater and it's easier to memorize. So this upside down triangle is called nabla, and do not get the wrong impression. This is not a Greek letter, although it might sound like a Greek letter if we call this, and of course not to my Greek listeners, but this is not a Greek letter, and it's also not a letter of any alphabet. It's somehow only the idea of at some point turning the capital delta, which would be a regular triangle, of turning this upside down. And the name nab, so this was just introduced as a symbol, I think, by Hamilton, the same Hamilton who was the physicist who created Hamiltonian mechanics. But later on then called nabla because this upside down triangle, which didn't have a name at first, this reminded someone, I think some philosopher or some theologist, called this nabla because there is a Phoenician harp in the Bible, an ancient musical instrument, the Phoenician harp, which is supposed to have looked a bit like this. And this Phoenician harp is in Greek called nabla. So a name of a harp that might or might not look like this symbol, that's why it's called nabla. But this is just for curiosity. Okay, so this is the gradient of f, and if it's partially differentiable everywhere, so partially differentiable, then if we take the whole as a function or as a map, the gradient of f is going from U to Rn, so at every point we have such a vector. This map is then simply called the gradient of f. Is called gradient of f without referring to a point. Okay. Now we've seen that this is so with the Jacobi matrix of the differential of f in A looks like this, only seen as a row vector. And from this you can make a very important or very simple observation. And sorry for the jump, made a little mistake. That n in M, U be an open subset of Rn as before. And this time we take a map from U to R, which is differentiable in a certain point A in U, then the differential of f in the point A applied to a vector v, how is this expressed in terms of the gradient? We have seen that for a function, or not only for a function, but there we have the sum of the partial derivatives times the coefficients of the vector. This was this corollary 1217, I think, in which we kind of expressed this relation and how we're going to compute a differential by its partial derivatives. Now, this sum formula that we had there has a nice, concise expression, namely this is nothing but the standard inner product of the gradient in A with the vector v. So this is the standard inner product that we always use all the time, which induces the Euclidean norm, and this holds for all v in Rn. And this is really a beautiful formula. So this is really how in a very concise way, the partial derivatives and the differential are related, right? So this is, and keep in mind, this is only defined for real functions, so for R-valued maps, because otherwise we don't have this gradient vector, but this is the way we describe it yet. So here, in this case, we can describe basically the whole differential by just describing one vector, this gradient vector. Okay, this is a beautiful relation, and yeah, there's actually nothing to prove, because this is just proof. This follows directly from this corollary, which describes the differential in terms of partial derivative. And let me look up its number. Yeah, 1217. From corollary 1217. So there's nothing more to show. Now, this is the direct relation here between gradient and differential. And the gradient is really useful and really has some interesting interpretations. Let me add a remark on the gradient. So remark 1234. So first of all, the first thing we want to observe is, so in this situation here, in corollary 1233, the existence of some vector which has this property. So the existence of some vector v0 in Rn such that the differential of f in the point A applied to v is equal to the inner product of this vector v0 with v for all v. So for all v. This follows in general, and this is what we already know for arbitrary inner products, and this is the Ries representation theorem. The differential is now a linear map from Rn to R, so an element of the dual space of Rn. And there we've seen, so for these dual spaces, that any linear map, or any element of the dual space can be written in this form: a fixed vector with the inner product with a fixed vector on arbitrary Euclidean vector spaces. Follows for arbitrary inner products from the Ries representation theorem. Which was in our numbering theorem 1028c. So in this way we could also define a gradient for arbitrary inner products, and in fact in several situations in calculus and geometry this is actually a really useful construction, but I will not go into details on this because we will restrict to the standard inner product. Okay, so this as a first observation, just for an abstract approach to the gradient. Now, the next I want to think a bit about the meaning of the gradient in terms of intuition and geometry. Namely, we want to consider first of all directional derivatives. So in the situation of the previous corollary again, so all quantities are defined as in that corollary. Then we take v in Rn and want to take the directional derivative in direction v. So we need a non-zero vector and we assume a bit more. We assume that this is supposed to have length 1. It's easy to see from the linearity properties of the differential. If we rescale the vector, if we multiply this by a constant, the value of the corresponding directional derivative gets multiplied by this constant, so we can always increase and shorten this. So it's interesting if we kind of keep the length fixed and see what then happens to directional derivatives in each direction. Now, assume we have length 1. Then we can compute the following. So the directional derivative of f in direction v, so basically the slope of the increase of the function in direction v, this is now, since we are in the differentiable setting here, this is, as we know, given by dfa of v, which is in turn, by the previous argument, the same as the gradient of f in a taken as the inner product here with v. So all inner products are all directional derivatives are just taken by inner products of the vectors with this particular gradient. What does this imply? This has an interesting consequence. Namely, if we use a bit of our knowledge of linear algebra, we have seen that the inner product is related to angles. And we had a relation about angles and inner products. And here, in fact, it turns out that this inner product is the same as, so the angle between the gradient and v. We have seen that the cosine of that angle is this inner product divided by the lengths of the vectors. Now, v has length 1, so there's only one length left, which means that this is the same as the norm of gradient f of a, so times norm v, which we don't, which is 1, times the cosine of the angle between these two vectors. Okay, this is what we have. Interesting. What does this mean? This gives us an idea about the directional derivatives, namely the value of the directional derivative, which is now really a real number, becomes maximal. So when do we get the biggest value for the derivative? We know, so this is some fixed number. This doesn't depend on the direction. And the cosine goes around between 1 and minus 1. So the biggest case is the case when the cosine is 1. But when is the cosine 1 for this angle here? It's only the case when the angle is 0. So it becomes maximal for the angle. So cosine of 0 is 1. So the angle between the gradient and v is 0. This means in turn, so they are linearly dependent, so to say, so they show in the same direction. So this means there exists some positive number, let's say lambda in 0 to plus infinity, with the gradient is lambda times v. Okay, what does this mean? Sorry. One particular case, one thing I need to assume in this construction, otherwise it doesn't make sense. We assume that the gradient is non-zero. So otherwise everything would be 0. This will be tackled in a bit. This becomes maximal, so for non-zero gradient, the case of gradient 0 comes in a bit, if they are linearly dependent. So this means this gradient here, so this is a positive number, so this gradient is really pointing in the same direction as v. So this means, i.e. this holds, i.e. if, and now this is a bit sloppy of course, the gradient points to the same direction as v. This means, since this is the case when the directional derivative becomes biggest when the gradient is pointing in that way. So this means the gradient is showing the direction where the derivative is the biggest, which means that the increase of the function in that point, the infinitesimal increase there, is the biggest. So nabla f of a points to the direction of, and now put this in quotation marks, fastest increase, I'm not very precise here in this, of f in A. So if we want to increase f very fastly, and if we are grammar, sorry. If we want to increase this as fast as possible and we're standing in A, this is the direction we have to run to get f bigger and bigger. Now, if we have this direction, then the norm of the gradient, so which is roughly the length of this vector of this gradient. If we take a look at this here, we see that in this case the cosine gets 1, this is what we saw, and then the derivative is precisely this norm. So, in other words, this norm is then precisely the value of this, of the partial derivative in that direction, and this means this is the precise value, and this can be seen as the rate of fastest increase. So how fast does it increase in the point A? So also this we can read off from the gradient. So basically the gradient tells us which is the fastest way to go to increase, the best way to go to increase f as fast as we can, and how far do we get, so how much does it increase. These observations are really useful because there are a lot of methods based on this. For example, in optimization of stuff, there are so-called gradient descent methods, where you basically, this is the main idea, you follow the direction of fastest increase or, so want to this to optimize, to maximize some given function to follow these directions there. And there are a lot of methods which are based on this thought and on this approach. So I'm not elaborating on this because this is not too relevant for you, but this is really, if you encounter this later on in some mathematical physics classes and so on, this will be, you will always there use these gradients. You will always see these gradients popping up anywhere. Okay, just one little example maybe, just sketch one so you get the idea. So yeah, this doesn't get even a number, just want to draw one simple picture. So let's take a function in two variables. F of xy is x squared plus y squared. And this is what I also discussed in the video where I presented some GeoGebra drawings to you. So the graph of this is a paraboloid. So in both coordinate planes, if x or y is 0, we get a parabola here. And this is kind of rotational symmetric, so this looks like this. So some parabola. And so we see if we're in a point, the fastest increase will kind of be always the one away from 0. So what does the gradient of this look like? If we take a separate coordinate system, a two-dimensional, so this is a map from R2 to R, so the gradient will associate a point in R2 with any point in R2. So at any point we'll have the gradient, and that's draw these here as vectors. We will first of all see in this point here, there's no increase, and we will indeed see that there the gradient vanishes. So here we would have just the 0 vector associated with 0. But if we go away from 0 in any arbitrary direction, because of the symmetry here, this will point away from 0. And remember, the length of the vector shows the rate of increase, and as we see, the further we get away from 0, the faster becomes the growth of the function. So this vector will become longer and longer and longer. And this is what you can do in every direction. So there you get some nice symmetry and some vectors here. This is also what you call a vector field, but I will not use this term in this class. And so on and so on, and this in all directions. Okay, so this all the way around, and this is how you see the gradient there. Okay, this took a lot of space, and now we've seen basically what we can do with the gradient if it's non-vanishing. The next we'll discuss the case which is vanishing, because there we will generalize the notion of local extrema. We've seen this in one variable before, and we have seen that for local extrema of the differentiable functions, the derivative is 0. And here we have the same way. So if we take a look at this example, this function has a minimum here. This function becomes 0 in the origin and is positive everywhere else. So this really has a minimum there. And as we will see then, this means that the gradient there is also disappearing. And we can tell from the gradient then if there is a local extremum. This is the necessary condition for local extremum then given by the gradient, as we shall see after I erased. We want to revisit the notion of local extrema of a function. We have seen this in Mathematics 1, where we have discussed local maxima and minima of functions defined on intervals. And basically the same definition, if you take a look at the definition from Math 1, I formulated it already in this way that it almost translates word by word to the current setting now, namely by the notion of a neighborhood, using it there. Let me first give you the general definition of local maximum and local minimum, and then we will see what how we can again say that a local maximum and minimum must have some, it's that the derivative of a function at the local maximum minimum must have some properties. Now, fine, let's take a look here at this. So, the definition 1235. So, we again study functions on open subsets. N in N, U in Rn be an open map. And to discuss local minima and maxima, it's important that we only discuss maps which map to R. So in Rn, so if we would have, like, for example, something which maps into the plane or something, then maximum and minimum just doesn't make sense. So maximum and minimum are only defined for real numbers. So we can only discuss this setting here, so functions from U to R, and assume we have some point x0 in U. Then f has a local maximum in x0, or, and let me put just the minimum case always in parentheses, so it's always not the parentheses, always the parentheses if you follow this argument here. So it's local maximum or local minimum in x0. If there exists a neighborhood of the point, a neighborhood A of x0, a neighborhood I've defined in the chapter on metric spaces. So this means we have small open subsets around x0 which is still included in there. For example, A could be an open ball around x0. So a neighborhood A of x0 such that it is a maximum in this neighborhood. So it's only if we restrict the function to that neighborhood, then we get a maximum or minimum. So this means local maximum, so only in with respect to all points in A it's a maximum, but globally of the whole function it might not be maximum or minimum. Okay, there exists a neighborhood A of x0 such that, and in the maximum case this means f of x is smaller than or equal to f of x0 for all x in A, and of course in the minimum it's just the opposite inequality. For the minimum case, f of x is bigger than or equal to f of x0 for all x in A. Okay, and this is almost the same as we had in the last semester when I had already introduced this term neighborhood in the complex numbers. Okay, this is local minimum or maximum in x0. Then the value, the number f of x0, this is a real number. This is then called a local minimum, local maximum or local minimum. So the minimum always refers to the value, right? This is just important to keep in mind. Local minimum of f. And the point is then called x0 is called a local maximum point. Or local minimum point. Of f. Okay. And we say that f has, just to summarize both cases, has a local extremum in x0 if just one of the two cases holds, if f has a local maximum or a local minimum in x0. Okay, a lot of terminology, but nothing very exciting. So now let's generalize this theorem about differentials or derivatives and local extrema, namely in the following settings. So before we had if a differentiable function on an interval with real values has a local extremum in some point, then the derivative is 0. Of course, here we have the more elaborate notions of partial derivatives, differential, and so on and so on. And it turns out we can really generalize this in a straightforward way to the setting, namely again, let n in n, u in Rn be open, f from u to r is supposed to be partially differentiable. So we do not need the full notion, it's just important, just enough to have partial differentiability. If f has a local extremum in a point, if f has a local extremum, in a point A in U, then it follows that the gradient vanishes in this point. Okay, and just by definition of the gradient, this just means that so if the gradient is the 0 vector, if and only if all partial derivatives are 0. So equivalently, if dif in A is 0 for all I between 1 and n. Okay. So this is again a necessary criterion, so this must necessarily hold, but as in the previous semester, if the derivative vanishes, we do not know yet if it has a minimum, a maximum, or nothing of the two. So it might be, anything might happen. So if you think of the function f of x is x3, this is an example where we have a point in 0 where the derivative vanishes, but it's not a local minimum or a maximum in there. So this might happen here as well. And as we've seen in the previous semester, we have used the second derivative then to clarify, or the higher derivatives. Also, if the second derivative vanishes, you can use the higher ones and so on, to clarify if the function has a minimum or maximum or not. This will work out the same way. The problem is we don't have higher derivatives yet. So we will need kind of the notion of the second differential and to see how kind of the higher derivatives generalize to differentials. This is what we will do in the next section, but for now, let's keep this again as a necessary criterion and let's prove this fact for the moment. So, the proof is actually not that difficult because we can just restrict everything to the one-dimensional case that we already know and use the one-dimensional theorem to show the general case. Okay, so assume without loss of generality that f has a local maximum. The minimum case is proven precisely the same way by just reversing some inequalities. So assume it is a local maximum in A. So we know it's a local maximum, so this means in the neighborhood of the point, it's a maximum. So this means, also since it's a neighborhood, there exists an epsilon ball in this neighborhood. So there exists an epsilon ball around this point, such that the restriction to the ball has a maximum in this point A. So let epsilon be bigger than 0, such that first of all, B epsilon of A is a subset of U, so it's well defined, and such that F is, A is the maximum of F in that ball, so F of X is smaller than or equal to F of A for all X in that ball. B epsilon of A. Okay. Now, we've got this, and so need to show that all the partial derivatives vanish, so that dif of A is 0 for all I between 1 and n. And to show that, we just think about how the partial derivatives were defined. The idea was we introduced certain curves and took the partial derivatives as derivatives of such curves. We can carry out this in the same way. So for each I, consider the following function, gi from minus epsilon epsilon to r, gi of t is defined as f of a plus t times ei, the ith canonical basis vector. Now, since this has norm 1, one can basically, one shows that this is well defined. Since, and this is a nice little computation, a plus t times ei always lies in the epsilon ball around a for all t between minus epsilon and epsilon, but here it's really important to take the same epsilon. Anyway, it's for us important is that we have some epsilon, and we know that f is partially differentiable, so since f is partially differentiable, we know that gi is differentiable, so gi is differentiable, and just by definition of the partial derivatives, gi prime of t is equal, the gi prime of 0 is equal to this ith partial derivative of f in A. This is by construction of the partial derivative. Just look up how we introduced them if you forgot the connection here, but this is just follows directly. Okay, this follows, but now, since they are all in this epsilon ball, we know that by construction, gi of t, this is f of some element in the ball, and there we know just by this property here that we chose, this is smaller than or equal to f of a, but this is by construction gi of 0. So this holds for all t in minus epsilon epsilon by construction, but this means 0 is a local maximum of gi. So a local maximum point of gi. So 0 is a local maximum point of gi. But gi, if we take a look at this, it's a differentiable function from an interval to r. This is precisely the case of mathematics 1. So this was Fermat's theorem in mathematics 1. This implies that gi prime of 0 must be 0, and since this is the partial derivative, this shows that the partial derivative in the ith component of f in A is 0, and this holds for all I in 1 to n, and this is what we wanted to show. So we could just restrict by taking nice curves to the one-dimensional setting. Okay, so just maybe I can draw a little diagram about this. So let's assume we have a graph, assume we have a function f from R2 to R. So its graph is something three-dimensional, as you can also see in the video about GeoGebra that I uploaded. Assume we have something like this. So assume the graph, the function would be defined on a circle, on the inside of a circle, on a disk there in R2, and assume this was here the graph in R3. I'm not drawing any axes at this point, and here we would have some local maximum. Assume this would be the point of this, so here we would have f of a. So the idea is now that we take the corresponding curves, and let me just draw it geometrically. So the two coordinate directions, so we would just maybe take this curve here, which follows that line here, assume the coordinates are in that situation, and further on here. And then go here in this direction and take there the curves as well. And as we see, the two curves F restricted to these parts here are just parabolas which have a maximum there. And then we're in the one-dimensional setting, and then we're done. So this is just the geometry behind this. Okay, so as I said, so far this is only a necessary condition for a local maximum or minimum, but we shall see later how we can decide if it's a local maximum or minimum or not, which requires a bit more preparations. Okay, the next up is a mean value theorem, but I'm not giving you the full or most general mean value theorem for Rn, since this is generally not very relevant for you. I mean, this might be useful in some situations, but just for time reason and not to go too much into detail because I would really have to introduce some more notions, but so just keep in mind there is a more general mean value theorem, but for practical purposes this should be enough. So namely a mean value theorem for real functions, meaning again mapping to R. Okay, so if I would have an audience, I would now ask you about the mean value theorem for mathematics 1. The idea was, let me scribble this here in the corner. If we have some differentiable map, say, f on some interval a, b to r differentiable, then there exists some element xi, which is somewhere in this interval I, a, b, such that, now I don't have enough space, great, f of b minus f of a is this derivative f prime of xi in this point xi times b minus a. There was some nice geometry behind this, so you could look at the second lines of the graph, but this, if you want to remember, just look at the video where I discussed this in Mathematics 1, which is still available. So this was the thing here. This is the same as the multiplication with the derivative of b minus a. Now, how do we get this to n dimension? The good news is in this version of the mean value theorem, that's really a straightforward generalization actually, namely again that n in n, that U be an open subset of Rn. We take a map which is differentiable on all of U, which maps to R. So this should be differentiable, and now let's assume we have some points A, B in U, and now we would have, now we need to find what is the generalization of this. There is some xi in this interval, so this interval, of course, this is not well defined yet, but here we have to make another assumption, namely we can kind of find an analog of this interval, such that the line segment which connects these two, the line segment, and by this I mean all points of this form, a plus t times b minus a in Rn, where t lies between 0 and 1, such that this set is completely contained in U. Meaning, let me scribble something here, so assume U is, I don't know, some particular form in R2, assume RU has this shape. Then if we take a point, let's say A here and B here, then you have, if you think about this, the equation, how it's defined, this set here is precisely this line segment connecting these two. This is described by that. And here we see that for these 2 points, a line segment would be completely contained. The question is, of course, what could go wrong? So assume we had some A prime and B prime. So assume here it's A prime, and here we would have some B prime. Then, of course, if you put in the line segment, this is no longer part of U. So here the assumptions are violated for this setting because this part of the line segment is outside of U. Okay, so we just need that this line segment is part of U, which seems like a quite mild assumption, I would at least say. Then, I want to give this a name. Sorry, line segment L. Then, okay, and now we need to, this multiplication with f prime, we have seen that this is kind of the one-dimensional version of the differential multiplication with f prime, and it turns out differential it is, we can really generalize it in this way, namely there exists some xi, which is now a point in this line segment, such that f of b minus f of a is the same as the differential of f in the point xi applied to the difference vector b minus a. This is the way how we can define this. This is now an equation of real numbers. So this is what we can do there. And as you might already imagine, we're kind of artificially building us an interval. And the idea is really to get back to the one-dimensional setting, and it turns out we can just, if we're smart enough, we can just prove it by applying the one-dimensional mean value theorem to get this simple result here. As I said, the most general version of the mean value theorem is quite more elaborate, but this is what I will leave away out of this lecture. So let's keep it at that, and let's prove this with using the one-dimensional case, but let me erase first and then we'll do so. The proof takes everything back to the one-dimensional case. Namely, we consider the curve which parametrizes this line segment between the 2 points, namely C going from 0, 1 to Rn. C of t is A plus t times B minus A. Now, if you take a look at the components of these, this is of course in sum of vectors, but if you take a look at the components, in each of the components there's just a linear function in t. This is obviously differentiable, so C is, first of all, just that this parameterizes a line segment. C of 0 is obviously A. C of 1 is A plus B minus A, which gives B. And C is differentiable with C prime of t, and this is derivative of a linear function, and you see that this is constant. This is just B minus A for all t between 0 and 1. Now, apply the mean value theorem from mathematics 1. So theorem 420. So apply this mean value theorem to the map F composed with C. F goes to R, C starts from 0, 1, so this is really a map from the interval 0, 1 to R. And this is now the application here. There exists a psi in the interval 0, I don't call this psi. There exists some t0 in the interval 0, 1, such that f of b minus f of a, which is, in terms of this composition here of f with c, this is f composed with c of 1 minus f composed with c of 0, and this is precisely the situation of the mean value theorem. Sorry, made a little mistake. This is then f composed with c prime in t0 times 1 minus 0, the endpoints of the interval, so just f composed with c prime of t0, but by the chain rule. This was the particular case of the chain rule that we had. This was corollary, this is the one I had stated explicitly, corollary 1229. This is df in the point c of t0 applied to c prime of t0, which is, by this computation, df in c of t0 applied to b minus a. So all that's left to do is we need to define xi correctly. We just need to put xi equal to be c of t0. This is for some point in u, and this is all we want. Not only in u, it's on the line segment L, which connects A and B, and this is what we wanted to show. So this proves already the mean value theorem by just tracing it back to the one-dimensional setting. Now, there was this assumption about the line segment, and of course we would like to apply this mean value theorem to a large subset, to a large set. And the notion for sets for which the line segments are again included gets a particular name, which I just want to briefly introduce, and not, this is some notion that I could talk about for one semester and do all the mathematics that's involved in there. Definition 1238. Let n be a natural number. A subset K of Rn is called convex. If for any 2 points the line segment is included. So if the set A plus t times B minus A in Rn, t in 0, 1, if this set is again in K, and if this is the case for all A and B in K. So for all 2 points, the line segment connecting them is also included. And as I said, I don't want to elaborate too long on this notion. Let me just use this definition in the next statement, but first give an example. As I said, convex sets, I could really easily talk for one semester only about convex subsets. They are extremely crucial for like optimization problems, and also in all kinds of algebra you need them, but anyway. So the example for this, first of all, R to the n itself is convex. This is of course obvious because by definition this is in Rn, so this is nothing new. But a more interesting example, the open ball of radius r around some point A, or the closed ball of radius r around A, are convex sets for all A in Rn and all r bigger than 0. Just a little sketch about this. So let's assume this is a ball. This would be a round thing. Here we would have a point A of radius r. Now, and since this is, the main idea is that if you take any 2 points here, the ball is bending to the outside, very roughly spoken. So here we would have a point, here we would have a point, then of course the line segments. This is something that intuitively is clear. So if I would take any 2 points inside this disk, the whole connection would be contained in there. So here we would have like some point x and y, and here we would have this line segment connecting them. In the same way, if we take any points anywhere, we would always have the setting that the line segments are in there. So this always works, and this works for open balls and for closed balls as well. I will leave it to you to prove this. This is actually a one-line proof, so it's not that hard. The drawing from the previous blackboard is not there anymore. There I had an example of a subset which is not convex because there was part of the connection line that was not in the set itself, but anyway, so this is a very simple example. Now, with the notion of convex subsets, this is basically the only relevant thing for us is now that we can then apply the mean value theorem at any point. And this leads to a nice little statement, which is not the most general statement of this form, but I'm only giving this statement because this is, otherwise I would have to put a lot more effort or some more terminology into this. So that, this is the wrong number, this 39, sorry, okay, I was just confused here by my own numbering, sorry. So n in n, and that U be a subset of Rn, which is open and convex. So we can apply the mean value theorem everywhere as soon as we have a nice function. And let's choose such a function, f from U to R, be differentiable everywhere. If the differential of f at any particular point is 0, so the 0 map, then f is constant, which again corresponds to the one-dimensional setting where we had seen that if the derivative vanishes everywhere, then the map is constant, as long as we are on an interval. So here it works in general for convex sets. The more general notion would be connected sets. I haven't defined connectedness in metric spaces or in normed vector spaces in general, but anyway. So here we get this statement that if the differential is 0, then f is constant, and the proof is now very easy. And we also derived this from the one-dimensional mean value theorem in Math 1, and here we will use the new mean value theorem to derive this statement for general arbitrary dimensions. So just by that mean value theorem, 1237, we would then get f of b minus f of a. If we would take some points a and b, then we would find something on the line segment connecting those two, which is contained because of convexity, such that, where's the state? No, don't have it anymore, but we would have the differential applied to b minus a. But if the differential is 0, this must be 0 for all a, b in k. And this, of course, means, f of a is f of b, and so f is constant. So we see that more and more properties from the one-dimensional setting are really transferred to the multivariable setting. But now if you might ask yourself, okay, why didn't we do everything in several variables in the first place? Why did we bother doing all this one-dimensional setting separately? Two answers. One of them, we are really everything doing based here on this one-dimensional setting, as you can see. Like here we used the one-dimensional mean value theorem, which we really proved explicitly, which was hard work. And there were several other statements where we always use statements from mathematics 1 for the one-dimensional setting to generalize this then to arbitrarily many variables. The second answer why we didn't start with this from the beginning is because it would have been very difficult. So there are some lecturers who start these calculus courses by doing analysis in several variables right from the start, but I think this is really a bit much in the beginning, actually, in mathematics 1. Okay. Now, the next notion. Let me first introduce a definition, which I haven't, about some terminology or some notion which I've used but not named yet. So this was, wait. So now the numbering is mixed up. This is not 39, this is 40. Oops. Okay, sorry about that. So this is definition 1241. Namely, we consider so that M and N and N, let U be an open subset of Rn, F from U to Rm. So we call F continuously differentiable, also generalizing a notion from before. So in the one-dimensional setting, we had that the derivative must be a continuous map, and here it's similar. We call F continuously differentiable if F is, first of all, partially differentiable, and if all the partial derivatives as maps are continuous. And we have seen already that if this is the case of continuous partial derivatives, then the map is differentiable. So it's continuous for all I between 1 and n. If this is the case, and so yeah, there we've seen by theorem 1218, it follows from this condition here that F is differentiable, so it really has a differential in every point. Okay, so much for that, but this is just what I want to call continuously differentiable. And we will need this notion quite a lot from what we're discussing next. Okay, now we're at, again, sorry, my numbering messed up, theorem 1242. Namely, this is again another generalizing statement. We want to study Lipschitz-continuity. I've introduced Lipschitz-continuity for metric spaces, and we've seen in Math 1, where we had just Lipschitz-continuity between the real and complex numbers, that any continuous map on a compact interval is Lipschitz-continuous. Here it's basically the same statement, namely the following, so that M and N and N, let U in Rn be open, and let F from U to Rm be continuously differentiable. So far the same conditions as in mathematics 1, except for the higher dimension. Now, if we take, almost, this is just an open set, but if we now take a subset of U, K subset of U is compact, and this is what we've learned in chapter 11, what compact is, and convex. Then the restriction of F to K, so as a map from K to Rm, is Lipschitz continuous. So just to recall, Lipschitz continuous means now there exists some constant such that the norm of f of x minus f of y is smaller than or equal to the constant times the norm of x minus y. And this for all x and y in K. Okay, this proof is a bit longer and I need some more space for this, so let me erase at this point and then do your proof in one go.